video 3 for day 3 notes. All right, to finish up histograms, we need to talk about the method for creating histograms with unequal classes, or we could talk about it, but we're going to skip it. If a frequency distribution has a non-bounded class, such as 12 or more, a histogram cannot be made. Think of the area principle. So that very last column would be wider than everything else, and then you would be breaking the area principle. So if we go back to day 1 in the class, we did the game agreed where we made a stem and leaf plot. So I'm going to go over this fairly quickly. And it's just another way to display data. Better if it's relatively small amounts because it's a pain to make for lots. So this side is the stem and this side is the leaf. And this one is already done for you. Please notice that I have a key, I can't say that enough, and a title. All right, the leaf should be single digits, no commas. And it's best if the leaves are in numerical order. If you put them out of order in this class, I will mark you wrong because it just adds extra information for you. And if you turn it on its side, you have a histogram. If it's out of order, you lose that extra information. Stem plots will look very similar to a dot plot or histogram of the same data, but a stem plot preserves the individual data values. This is super important. Here, I know that one student is exactly 97 pounds. While up here, I knew somebody weighed a little less than 58, but I didn't know exactly. So you actually get the raw data with the stem and leaf plot. And then if you remember, on the first day we also did a back-to-back stem and leaf plot, which we used to compare. So if we wanted to compare the girl data to the boys, we could then plot the 93 and the 99. And we had another girl, 100, 104, 109. I'm not going to do it all because I'm confident you could do that, but you could see how it'd be easier to compare. And again, you'd want to have them probably in the same font and everything, because then it's easy to see how much taller. This doesn't look quite as tall as 3 there, so you'd want to have them in the same layout. Here's something new. When a data set is very compact, it is often useful excuse me, I had to pause. It is often useful to repeat stems to stretch out the data. So let me show you. If we were to take this body temperature data I've already labeled, our stems would be 96, 97, 98, and 99. And then we have 96.3, 0.6, 8, 9, 98.1, 1, 3, 5, 6, 6, 7, and 8, and 99.0 and 5. It's there's a lot of numbers here. And we're only between 4 degrees, so it might be helpful to break it up. So I'm going to look at it here. Instead, I'm going to do 96 degrees low and 96 degrees high. And by that I mean 96.0 up to, including 96.0 up to, but not including 96.5. And then for the high, 96.5, include that, but go up to, but not including 97. So if I redo that, I've got low and high. I would need to redo my key and to label it, but I'm sure all of you can do that. 97, 98, 98, 99, 99. So I have 3, 6, 8, 9, and I am still just getting them. Oops, that's 97, excuse me. 6, 8, 9, I'm still just getting them off of there. 1, 1, 3, 5, 6, 7, 8, 0, and 5. And what we actually catch here is that there's a gap right here, which might be useful if we weren't trying to interpret this data. Okay, this is sometimes called a split stem and leaf plot, or a split stem plot. Okay, we can also go the other way and we can truncate. Okay, so the opposite would be to truncate the data. And in this case, we would have lots of stems. 10, 11, 12, 13, 14, 15, 16, all the way up to $52, which would be a little bit of a pain. And then it would even be worse because we can only have single digits, so we'd actually have to do 10, 10.1, so you could have the 3 there. And then we'd have to have 10.2, 10.3, 10.4, and we'd have to go all the way up to 13.6 before we even got another data point. So one nice or easy way to truncate it would be just to at least, they just have you cut it off. You can round or truncate. But truncating means that instead of rounding this to 20.9, you just do 20.8. You can decide if you want to round or truncate, but you have to tell whoever it is in your key. And then, at least it's a little bit easier over here, and you can just go 10.5, 13.6. I honestly won't ever give you anything where you need to do that. All right, guys, we're almost done. Now we just need to talk about the 4 key features of a distribution. Okay, and you really should have these memorized. It is shape, center, spread, and unusual values. Maybe somebody can come up with an acronym for this. Okay. So, and then we have lots of words to describe the shape of a distribution, such as symmetric. I'm going to write them down and go over them. Single peaked, double peaked, skewed left, skewed right, and uniform. I guess we'll just put uniform in right there. All right, so symmetric is just what it says. The distribution would kind of fold in half and have a piece of symmetry. Single peaked, we've got one mode, or one, if we have data that's doing this, one really high middle peak. Okay, double peaked, just what you would guess. Okay, we've got 2 modes. This one and this one. Skewed left is kind of the opposite of what you might think. Okay, it means most of the data is to the right, but you have a tail out here of some outlier or some low value that's skewing it. Skewed right's the opposite. And uniform, everything is pretty much the same. And we'll go over these again in class. Next thing we're going to talk about, center is obviously where the center is. Spread, it'll be from the low to high value, and we'll talk about that. And now we're going to talk about unusual values. Okay, there are some things to consider with unusual values. Outliers, or things that are way far from the rest of the data. Clusters, stuff that's grouped together. And gaps, large spaces. So I'm just going to quickly go over some unusual value stuff to end us off. I don't know if you guys know who Usain Bolt is, but he's an outlier, okay? Here's a bunch of really Olympic quality athletes and their times doing the 200-meter dash. And he is all the way over here. So the person before him was Michael Johnson in 1960, and Usain Bolt is all the way over here. Some people like to throw out outliers, but really, oftentimes that's where the most interesting data is, so you don't always just want to throw them out. Sometimes it could be bad collection of your data, but in this case, these two are just amazing, and they're the most interesting part. Here's the last part. So bottom line is it's extremely important to investigate outliers. All outliers should be taken seriously. All outliers should be taken seriously and should be investigated thoroughly for explanations. Okay, automatic outlier rejection schemes, such as throughout all data beyond 4 sample standard deviations, and we'll talk about that, are particularly dangerous. The classic case of automatic outlier rejection becoming automatic information rejection was the South Pole ozone depletion problem. Ozone depletion over the South Pole would have been detected years earlier, except for the fact that the satellite data recording the low ozone readings had outlier rejection code that automatically screened out the outliers, that is, the low ozone readings, and basically threw them away before they did any analysis. Such inadvertent and incorrect purging went on for years. It was not until ground-based South Pole readings started detecting low ozone readings that someone decided to double check as to why the satellite had not picked it up. In fact, it had, but everything had been gotten thrown out. So the best attitude about outliers is they are our friends. They're trying to tell us something, and we should not stop until we are comfortable in the explanation of each outlier. Oftentimes, we will present data with and without the outliers so that we can compare. And yes, sometimes there are mistakes in data collection, but also sometimes they're the most important stuff.